Hello everyone, welcome back. My name is Mr. Kowald, and in this video I'm going to show you how to write the molecular, complete ionic, and net ionic equations for the reaction of copper-II chloride with potassium sulfate. So let's get into this. Okay, so we have our copper-II chloride with potassium sulfate, and we're told that it yields a clear blue solution. Okay, so what's that all about? So when we're writing our molecular equation, we need to convert. It looks like they've given us the names of the formulas. And so what you need to be able to do is to convert the names into the formulas. So if you don't know how to do that, please check out my video on naming ionic compounds and how to go from formulas to names, names to formulas. But I'm going to kind of go through that in this video as well. So the name of the formula is giving you the names of the ions. So if you know that the name of your compound is just the names of the ions together, then you can break it back apart. So the first one is the copper-II ion, and we got the chloride ion. So we need to be able to write the formula as well as the charges. So copper-II is Cu is copper. The Roman numeral is telling you the charge. It does not tell you how many copper ions I have in my compound. It's just the charge on the copper atom. So it's a 2 plus charge. So that's going to be a 2 plus. And so this is my first ion. And my second ion is the chloride ion. Chlorine is in group 7, so we know that it has a -1 charge. How do we know that it has a -1 charge? Well, there's a couple of ways that you can know that. One, if you know the rule that if you are in groups 5A to 8A, if you're in those groups, then you could follow the rule of the group number minus 8 gives you the charge in that group. So this only works for those groups, and it's the main group elements that we're looking at. So we're looking at the A group, so 5A to 8A. So that's one way to think about it. So if you're in group 5A, then 5 minus 8 is -3. If you're in group 7, then it would be 7 minus 8 gives you -1. And so chlorine is in group number 7, so it's a -1 charge. The better way to remember this is to think about the valence electrons that you have. So remember the group number in the main group elements, so 8, A1A through 8A, those numbers tell you the number of valence electrons. So if you're in group 8, then you have 8 valence electrons. If you are in group 3A, then you have 3 valence electrons. So chlorine is in group 8, group 7. So it's the halides group. So all of those in group 7 are going to have 7 valence electrons. And remember, all atoms want to have a noble gas configuration. They want to be like noble gases, and noble gases has a full outer shell, and that's normally 8 electrons. So since chlorine has 7 valence electrons, it only needs one more electron to be like a noble gas. So it's going to get that one negative electron, and when it does get that negative electron, it gets that one negative charge. So that's why chlorine has a -1 charge. So either way, we know that the chloride ion is going to have a -1 charge. And so we know right away that here, this is -1. When you're writing the formula for your compound, your ionic compound, you need to make sure that the compound is neutral, that the charges are balanced, negative and positive is balanced. And we can see here that copper is a +2, chloride ion is a -1. So we need 2 chloride ions to balance the charge of 1 copper ion. So it's 2 to 1. Another way is to use the crisscross method. So the crisscross method, this number I put as a subscript over there. The 1 over here I put as a subscript there, and I get my formula. So either way, it's going to be Cu and Cl2. So that's my first substance, okay? And I do the exact same thing with potassium sulfate. So potassium is K. It's in group 1. So for groups 1A through 3A, the rule is the group number is the same as the positive charge. So since potassium is in group 1, it has a +1 charge. Also, the better way to think about it is Since potassium is in group 1, it only has one valence electron, so it's really easy to lose that one electron. So it's going to lose that negative electron, and then once it loses that electron, the balance of the protons and electrons is no longer there. So you're going to have one proton that is no longer balanced by the negative electron. So that's where the positive 1 comes in. So you got a +1. Sulfate is a polyatomic ion. You got to know your polyatomic ions. I'm sure your teacher gave you a sheet of paper with the polyatomic ions to remember. I have a YouTube video that goes over how to remember your polyatomic ions. I give you patterns to follow that helps make it easier to remember. Check out that video if you want to know how to do that. But you need to know what sulfate is. So you need to know that it is SO4, and it's got a 2- charge. And so I see that this is a 2- charge, and it's got a +1 charge for the potassium. So that means I'm going to need 2 potassium to balance the charge on the sulfate. So the formula is going to be K2SO4. So there's the formula of my second reactant. So now that I have my reactants, all I need to do is now figure out what the possible products are. And right away, you can see that this is a double displacement reaction because I have 2 ionic substances. And that's a dead giveaway for a double displacement reaction. So now how do I figure out my products from a double displacement reaction? I do the inside ions, I put those together. I do the outside ions, I put those together. And I balance the charges on the product side. And so that's what I'm going to do. So I got my arrow. So the inside ions go together. So chloride is going to go with the potassium. And then my copper-II ion is going to go with the sulfate. So copper-II with sulfate. So remember, copper-II has a +2 charge. Sulfate has a -2 charge. So they have equal charges. So I only need one each to balance the charge. So that's going to be CuSO4. And then for my other possible product, I have potassium and chloride ion. So potassium has a +1 charge, chloride has a -1 charge. So again, it's going to be a 1-to-1. I only need one each to balance. So that's going to be potassium KCl. And again, the positive ions are always written first. Okay, so now all I need to do is balance the equation and figure out what the states of matter are. So here I have 1 copper, so that's balanced. I have potassium. I have 2 potassium, but I only have 1 over here, so I'm going to need to put a 2 coefficient. And I have 2 chloride ions. Now I have 2 chloride ions here, and I have 1 sulfate and 1 sulfate. So this is balanced. Good. So the last step is to figure out the states of matter, and that is where you're going to need your solubility table. So either I'm sure your teacher gave you one, or there's one in the book that you have or that you're using, or you can find it easily on the internet. Either way, you're going to need to know the rules. Maybe you got it memorized. So either way, we're going to have to figure this out. So chloride ions. The rule for chloride ions is that they are soluble unless you are paired with one of these metal ions, which would be your silver ion, your lead-2 ion, or your mercury-1 ion. So it looks like we have copper, so we don't have any of those exceptions. So this is going to be soluble. So it's aqueous, dissolved in water. So AQ. Sulfates. The rule is sulfates tend to be soluble in water. So it looks like for the rules, it says all sulfates are soluble in water except for silver, lead-2, and a host of other exceptions. They can be insoluble also, unless you have a group 1 element. We have a group 1 element, so this is definitely going to be soluble. So this is AQ, soluble in water. And what about copper sulfate? So again, sulfates, it says sulfates are soluble in water unless you have silver, lead 2 ion. It looks like a mercury 1 ion, barium, strontium, and calcium. So it looks like, again, we don't have those exceptions. So this is going to be soluble in water. So that's AQ, soluble in water. And again, we have a chloride ion, and chlorides are soluble in water unless you have silver, lead 2, or your mercury 1 ion. So we don't have that. We have potassium, so that's going to be soluble as well. So that's AQ. So it looks like everything is soluble in water. And so once you get that, you want to pay attention to the fact that we have aqueous for everything, and everything is ionic. So what does that mean? That means that this here, when mixed with this, doesn't do anything. Why is that? Well, let's go to the next one and write out our complete ionic equation. So here we have our balanced molecular equation. Let's write out the complete ionic equation and we'll kind of see what's going on here. So here, the way you write out your complete ionic equation is everything that is aqueous is pulled apart. So when you have an aqueous ionic substance, what does that mean? It means that these ions are actually not together. They're actually separated from each other in water. So the way we write this here, like it's like a molecule, that's why we call it the molecular equation. We're putting the ions together in a formula as if they're together like a molecule, but they're not together in reality. So the complete ionic equation shows that more clearly. So we're going to separate out the ions as they really are. So these ions are going to be separated. So we have the copper, and we're going to write the charges as well. So when we separate the ions, we write the charges with the state of matter. So I have one here, so that's a 2 plus aqueous. And then I have 2 chloride ions. These 2 chloride ions are not together. So if I write Cl2 like that with a minus charge, what I'm saying here is that this is a molecule of chlorine and it has a negative charge, but that's not what we want. We want to say that there's 2 chloride ions. So this is not the formula. We're not going to keep the subscripts. So anytime you have a subscript with your ion, we're going to make that as a coefficient. So we're going to add plus, and that's going to become a 2. So the subscript becomes a 2. So we're going to have Cl minus aqueous. And then we're going to do the same thing for our potassium sulfate. So again, we have 2 potassiums. So that's going to be a 2K plus aqueous. And then we got 1 sulfate. The 4 is here. We're not going to write that as a 4 because the 4 there is part of the complete whole. So this is like, think of this as a molecule with charge. So this is not separate. So this is actually 1. So we're going to put a plus SO4 2 minus, and that's aqueous. And then we're going to do the same thing for our products. So this is going to come apart. So we got 1 copper. So this is Cu2 plus aqueous. And then we got our sulfate. So we're going to add that. So we got 1 sulfate, SO4 2 minus aqueous, plus, and then we put this apart. Now we have 2 potassium chlorides. So that means we have 2 potassiums and 2 chloride ions. So we're going to have 2 potassium plus aqueous plus 2 Cl minus aqueous. And so this here, ladies and gentlemen, is our complete ionic reaction. So this is the complete ionic equation. And so now you can kind of see what's going on here. So if these two ions are in one beaker, so let's pretend this is our one beaker, and this here is our second beaker. So here I have my two beakers. In this beaker, I have ions that are aqueous. They're floating around, separated from each other. Here I have another beaker separated from this, and these ions are separated, and they're floating around doing nothing. And then what happens? I put them together in the beaker. So I take the two beakers, right, and I pour them into another container, and now I get all of the ions floating around. And guess what? They're all aqueous. So that means they're floating around still. So before I mix them around, they're floating around doing nothing. And then after I mix them, they're still floating around doing nothing. So nothing's happening. So this is a no reaction. So no reaction. So normally when I do my net ionic equation, you want to remove the spectator ions. And remember, the spectator ions are the ones that are involved or are not involved in the reaction. So any ions that are coming together to form, like say, a solid precipitate or a gas or liquid or something like that, those are going to be part of the reaction, and so those are not spectator ions. But here, uh, kind of, you could see two ways. One, if we had a solid here, you could see what ions are involved in the solid, and then everyone else that is not involved in that solid would be spectator ions, and you get rid of those. The other way is you could see what stays the same on both sides of the equation. So if you have an aqueous here and it stays aqueous over here, it's not part of the reaction. So what you'll notice here is that everything on this side is aqueous, and then everything is the same on that side. So everyone is a spectator, no reaction. I hope this made sense. If you enjoyed this video, if it really helped you, I hope you'll hit the like button, share it with your friends, put a comment down in the comment section. Let me know what you think. If you have any other questions or if you have another problem you want me to go over, I'll be happy to do that. Thanks for joining me. Oh, and by the way, subscribe to the channel, hit that notification bell so you can get notified of other videos. Thanks for joining me. Have a great day.